remember that relative to a basis B consisting of vectors v1, v2 in this order, the vector a1, a2, the column vector a1, a2 means, and let me just, a little redundant, but I'm going to write the B here. A1, A2 relative to B means simply A1 times your V1 vector plus A2 times your V2 vector. So you've got your basis, you've got your V1 and your V2, and you can have vectors A2 V2 plus A1 V1. Now A1 would be negative in this case, and those two vectors would go together to give you a resultant vector A1 V1 plus A2 V2. Might be a little hard to read that, but it's a reminder, something you should know at this point, but something we don't always keep in mind. Okay, so now we postulate that we have a basis B consisting of 0.6, 0.8, and 0.8, negative 0.6. Now these happen to be unit vectors, as you can easily verify, and they're also orthogonal. Okay, that is, if I do the dot product of this with this, I get 0. I get 0.48 here, I get negative 0.48 multiplying the second coordinates, they add up to 0. Okay, so we have a basis B consisting of these eigenvectors, and they happen to be orthogonal unit vectors, which means this is what we call an orthonormal basis. I'm not going to write that term down here, we're going to use it plenty of times in the future. So then we have a transformation, okay? Relative to basis B, you got some matrix A sub B that transforms a vector relative to B to another vector relative to B. Well, if B is an eigenvector basis, then this matrix has to multiply this vector by some number, which would be the eigenvalue for this eigenvector, and this vector by some eigenvalue. Might be the same, might be a different eigenvalue. Because of what we're saying here, this matrix would have to be diagonal, because the vector, let's say 1, 0, relative to this basis, would just mean the vector v1, wouldn't it? Because you'd have 1 times v1 plus 0 times v2. If this vector is, as it is here, an eigenvector, then when you do the transformation on 1, 0, you're going to get lambda 1 times v1, where lambda 1 is the eigenvalue of vector v1. And if you transform 0, 1, you're going to get 0 v1 plus a multiple of v2, and that multiple of v2 has to be the eigenvector for v2. So that would be lambda 2 v2. The matrix that maps this, that would map 1, 0 onto lambda 1 v1 and 0, 1 onto lambda 2 v2 is just the matrix with lambda 1 and lambda 2 on the diagonals. And you can verify that, you can read about it, you can see where we've worked that out in past examples. Okay, so this is a diagonal matrix. Okay, here's your standard here's your eigenvector basis, and now we want to see what the matrix would be if we map this according to the standard basis. In other words, if we take the vector 3, 6 down here, what is that going to map to over here? Well, we take that vector 3, 6, and back up a second. If we know the matrix that takes a vector from basis B and represents it according to the standard basis, we're going to call that the P matrix. Okay? And because of everything we've said here, and we've talked about it again previously, the P matrix is just your column of eigenvectors matrix. So the P matrix is just going to have these two eigenvectors in the column. So if you have a vector up here, it corresponds to the vector that you get when you multiply the components of this vector by this matrix. Okay, now, if we got like 3, 6 over here and we want to know where it goes over here, then we can take the inverse of the P matrix and map that 3, 6 vector up to whatever it maps to up here. We can map it across here using our diagonal matrix, and then we can bring it back down here with our P matrix. And it follows then, as we've seen before, but we want to keep explaining this, that this A matrix is what you get when you start with the inverse of the P matrix. Multiply then on the left, and you multiply your vector on the left by the inverse of the P matrix. You multiply that result on the left by the diagonal matrix, and you multiply that on the left by your P matrix. So that the A matrix is going to be P times A sub B times P inverse. Now, for an orthonormal or orthogonal matrix, we just call it orthogonal, orthogonal vectors just have to be perpendicular. An orthogonal matrix has to consist of perpendicular columns that comprise perpendicular vectors that are also unit vectors. So, it's not that hard to prove that the inverse of an orthogonal matrix, a matrix consisting of orthogonal unit vectors, whose columns are orthogonal unit vectors, is equal to the transpose. Fairly easy to verify for any given matrix, and pretty easy to show. Okay? In any case, the inverse then is the transpose of the P matrix, which means we just switch rows and columns, and it turns out that since this matrix happens to be symmetric, switching row and columns gives us the same matrix. That won't always be the case. Okay, but in this case it is. And don't confuse the fact that this one turns out happens to be symmetric with the fact that this A matrix has got to be symmetric. That has nothing to do with the fact that in this case the P matrix is symmetric. Doesn't matter whether the P matrix is symmetric or not, as long as it's orthogonal. In any case, the A matrix then is this, and we can calculate that for diagonal matrix 2, -1. And what's this mean again? This means that the eigenvalue of this vector will be 2. So that means that we're mapping the vector 6, 8 onto double 6, 8, which would be what? 1.2, 1.6. So the vector 0.6, 0.8 then, by this transformation, gets stretched out by a factor of 2. Okay, and then the -1 here means that your second vector is going to be multiplied by -1 when you do the transformation. That means that the vector 0.8, -0.6, which kind of goes in this direction, would get reversed, but without changing its length. Okay, so we've got this mapping that accomplishes that, and that's assured by this matrix here and these two eigenvectors. Okay. The A matrix for that particular transformation, calculated using the P, A, B, and P inverse matrix as we just discussed. Well, we just write it out, we do the calculations, and here's what we get. And how about that? This matrix is symmetric. Now, it's symmetric because this is an orthogonal matrix, not because this matrix is symmetric. And actually, yeah, it is symmetric. Okay, but that has nothing to do with the fact that this is symmetric. Any basis, any orthogonal matrix here, meaning that you have eigenvectors that are the columns of the orthogonal matrix, will result in a symmetric matrix when you do this. Okay, so we come down to the conclusion that if A is symmetric, well, no, we don't get that conclusion. We can't draw a conclusion from one example in any case. This is a plausibility argument. It shows that in this case the matrix is symmetric. There is also the statement that's not proven by this statement by any means, because it's the converse of the fact that when you do this with an orthogonal matrix here, you get a symmetric matrix. The other is, if you start with a symmetric matrix, then you're going to get a set of orthogonal eigenvectors. Now, I say orthogonal, okay, that's orthonormal. And I didn't read this right. It says if A is symmetric, there is a set of orthonormal eigenvectors that diagonalize the matrix. Now, what I was about to say and what I thought I was going to read here, and I read something different. I can say if A is symmetric, then its eigenvectors are orthogonal. Okay? So when you find the eigenvectors of a symmetric matrix, you're always going to get a set of orthogonal eigenvectors. You can take their dot products with one another and verify that they're orthogonal. And if they aren't, then you did something wrong. They won't necessarily be orthonormal, because orthonormal means that the vectors are not only orthogonal, but they're all unit vectors. Now, if you've got a set of orthogonal vectors, you can make them orthonormal. You just divide each vector by its magnitude, and there it is. Okay? There's a little more to it. I can say, I don't really have room to write it, I'll just say it. Its set of eigenvectors is complete. If you have a symmetric matrix, you have a complete set of eigenvectors. Now, a symmetric matrix has to be square, and it's not necessarily 3 by 3. It could be 2 by 2, 3 by 3, 4 by 4, n by n. This means that if you find the eigenvectors of a symmetric matrix, an n by n symmetric matrix, let's say, you're going to get n distinct eigenvectors, and mutually orthogonal eigenvectors. And you can then normalize them. You have an orthonormal set. And then you can use that orthonormal set to just write down the columns of that. Well, you write down the orthonormal set, okay, like this. But if there's, if it's a 12 by 12 matrix, you're going to have 12 of them. They're all going to be 12 numbers long, bigger columns. You're going to have this matrix here that just consists of those column matrices. And this matrix and its inverse, which is just its transpose, allow you to diagonalize the matrix. Okay? And I'll just write it down and you can ponder it. A sub B is P inverse A P, which is P transpose A P. That is, if A is a symmetric matrix. So, you've got a symmetric matrix, find its eigenvalues, find its eigenvectors, put them in a column, you got the P matrix. Do this calculation, which is the same as this calculation, using the A matrix, the P matrix, and its transpose, and you get a diagonal matrix. And now you have an orthonormal basis, which is very convenient for many reasons.